Hey everyone, and welcome to Chem Talk. In this video, we'll be going over gas laws and detailing a few practice problems as well. We'll finish up by understanding how medical professionals use these gas laws to save lives. Gases are always surrounding us. Our entire atmosphere is gas, and any air that we breathe in are gaseous molecules. Only in the vacuum of space is there truly a lack of gas and gaseous molecules. To better understand our environment and how gases react to changing conditions, we need to understand gas laws. In this video, we'll go over how these gas laws, as well as how they are applied in the operating room by anesthesiologists. Ideal gas laws are equations that establish relationships between four different variables: temperature, pressure, moles, and volume. However, this formula is based on these gases behaving ideally. So there are a set of assumptions that we have to make when we say a gas is ideal. These four main assumptions are as follows. Number one, the gas particles are of negligible volume. That means they don't have volume. They don't take up space in space. Number two, the gas particles are of equal size and don't have intermolecular forces with other gas particles. Number three, the gas particles move randomly in agreement with Newton's laws of motion. And lastly, number four, the gas particles have perfectly elastic collisions with no energy loss, like to heat. In reality, there are no truly ideal gases. So let's look at these assumptions and decide whether they exist in the real world. So starting at assumption number one, that the gas particles must be negligible in volume. And we know this isn't true. Gas molecules have a volume. They take up space in the world. So right off the bat, that is not true. That breaks one of our first assumptions of an ideal gas. Moving on to assumption two, that the gas particles must be of all equal size and have no intermolecular forces. And this isn't true in the real world. Gas particles are of all different sizes. You have hydrogen gas, H2, two hydrogen atoms. Compare that to chlorine gas, two chlorine atoms. Chlorine is much bigger gas. So therefore, we know this isn't true. And there's constantly intermolecular forces going on between these. Depending on how big they are, it changes. Moving on to assumption three, that gaseous particles move randomly according to Newton's laws. Well, this is true. Molecules do follow Newton's laws of motion. So that's score one for us. Move on to assumption four. The gas particles must be perfectly elastic collisions. Well, this isn't true. As we mentioned before, during collisions, there's heat created between these molecules. Maybe there's a slight little amount, but there is heat created, which slows down, which means these aren't perfectly elastic collisions. So 3 out of the 4 assumptions of an ideal gas does not exist in the real world. However, despite ideal gases not being possible in the real world, the ideal gas laws act as a versatile guide for the calculations of gases. Scientists often use gas laws as an approximation for more rigorous, intensive calculations. If an exact calculation is needed, other methods may be used. However, the ideal gas laws are still an accurate representation of a large amount of models. The main equation we'll be dealing with is the ideal gas law, also shown as PV equals nRT, or PERF for short, where P equals pressure in atmosphere units, V is volume in liters, N is the amount of molecules in moles, R is a gas constant, and T is temperature in Kelvin. The units we use in the Pervner equation are incredibly important. Pressure must be in atmosphere units, or ATMs. Volume must be in liters, not milliliters, liters. And temperature must be in Kelvin. And finally, R. R is the ideal gas constant. This balances units on each side of the equal sign. R is equal to 0.0821 liters atmosphere per mole Kelvin. It's the constant that relates all these variables together in an accurate way. Using this Pervner equation, we're able to find the missing information. For example, if we know 3 out of the 4 variables, we can find the 4th. For example, if we know pressure, volume, and temperature, then we can find the number of moles of gas within the container. Let's look at a few examples of this. What is the pressure in the container given there are 5 moles of H2 in a 3-liter container at 20 degrees Celsius? So to start out, we're going to write out the Pervner equation. PV equals nRT. And we're going to see what we have. We have moles, 5 moles of H2 gas. We have volume in 3 liters. And we have temperature in 20 degrees Celsius. So from here, we're going to plug in what we know. We don't know the pressure, and that's what it's asking us for to solve. We know the volume, 3 liters. We know the moles, it gives us that in 5 moles. And we know the R value, which R equals 0.0821. I'm going to leave the units out for now. 0.0821 and the R value. Now for temperature, we have to remember temperature must be in Kelvin. So the conversion from Celsius to Kelvin is you have to add 273 to Celsius to get the number for Kelvin. So 20 plus 273 is 293 Kelvin. And from there, we know our missing variable, P, for pressure. All we have to do is move the volume to the other side of the equation sign by dividing by itself and then solve for pressure. Now, I've already done this, but you can stop here and do the math. But we found that pressure equals around 40.1 atmospheres. Determine the volume occupied by 4 grams of carbon dioxide at STP. So STP is language that's used in a lot of these problems. STP is an acronym that stands for Standard Temperature and Pressure. All you really need to know is that at standard temperature and pressure, the pressure is equal to 1 atmosphere, or 1 ATM, and the temperature is equal to 0 degrees Celsius, or 273 degrees, or 273 Kelvin. In using that information, this is just as similar as the last problem. It is very plug and chug, Pervner. Pressure times volume equals nRT. Alright, so what are we trying to solve? We're trying to solve for volume. What do we have so far? We have pressure, which is at 1 ATM. We're trying to solve for volume. We don't know moles yet, so I'll leave it blank. But we do know R, which is 0.0821, and we know temperature, which at STP is 273 Kelvin. So now we need to solve for moles. So for 4 grams of carbon dioxide, we need to know the molecular weight, because we need to get grams to moles. So the molecular weight of carbon dioxide is around 44 grams per 1 mole of CO2. And that means 4 grams of CO2 is roughly 0.091 moles of CO2. And from there, we can plug the moles back into our equation. So our volume is equal to 0.091 moles. And then we fill out the rest of the equation. And from here, you can solve it on your own. I know the answer right now, but you can pause the video, solve it on your own, figure out, and then you can check back. But the answer is the volume is around 2.04 liters. Remember, this is in liters because this is Pervnert, and we're using the gas constant, which is in liters. Pervnert can be used as a starting point for other gas laws. The first of which we'll talk about is Boyle's gas law, which relates pressure and volume at a constant temperature and amount of gas. On one side of the equation, you have the original conditions, or P1 or V1, the original pressure and volume in the container. And for this, we'll say this is at 1 atm or 1 atmosphere and 1 liter for volume. Now, to equal this on the other side, we'll say we are going to decrease the volume of the container. However, to make sure it is equal, we have to also increase the pressure at the same time. So if we're decreasing the volume to say 0.5 liters, the pressure must also increase in the final condition because you're squishing down the amount of gas that is in that container. This is the essence of Boyle's law. You have a starting condition on the left side and you have the final condition on the right side. And they're equal to each other. So if pressure goes down, then volume must increase. If volume goes down, then pressure must increase. Let's look at an example problem. What is the final volume of a balloon that is originally 2 liters at 4.5 atmospheres is now at 1.5 atmospheres? So let's remember, this is Boyle's law, so let's write out our equation. Pressure 1, V1 equals pressure 2 and volume 2. All right, so what is our original conditions? Let's see. It tells us we have 2 liters at 4.5 atmospheres. So let's fill that out for our original conditions. Let's see, pressure is 4.5 atmospheres times 2 liters and equal to, and now what is our final conditions? And it tells us that now the pressure is 1.5 atmospheres. All right, so we're solving for the volume of the final balloon or final container. So now we know we have to move the variable that we're solving for all on its own on one side of the equal sign. So how do we do this? We move the 1.5 over. So we divide by it on the right side, and we have to divide by it on the left side. Anything we do to one side, we have to do to the other. All right, so now we have V equals 4.5 times 2 over 1.5. If we just do the top side first, 4.5 times 2 is 9. Then divide by 1.5. You can do this math on your own. But the new volume is equal to 6 liters. Similarly to Boyle's law, Charles' law is derived from the ideal gas law, or Pervnert. Charles' law has pressure in moles at a constant, which leaves us with volume and temperature. I like to think of Charles' law through the lens of a balloon. The greater the temperature, the greater the volume will be. For example, on the left side of the equation, you have V1 over T1 equals, and on the right side, you have V2 over T2. So if we look at this, you have the original conditions on the left balloon. On the right balloon, if you increase the temperature, the volume also has to increase. The temperature speeds up the movement of molecules or gaseous molecules within the balloon, which then increases the force of which those molecules move and the energy those molecules have, hitting the sides of the container. This will cause further expansion of the balloon, making the volume bigger. Let's look at an example. What was the temperature of container given it originally held 300 milliliters and is now 500 milliliters at 30 degrees Celsius? All right, so in this problem, we're given volume and we're given temperature. So we know this is going to be Charles' law. All right, so we're going to write out the Charles' law equation. Let's see, it is V1 over T1 equals V2 over T2. All right, and then what do we know? We know originally our volume was 300 milliliters, and we're trying to solve for what was the original temperature. So we're trying to solve for T1. All right, and what do they give us now? They give us that now we're at 500 milliliters, so that's our volume 2, and we're given that it's at 30 degrees Celsius. All right, so now we just need to get the unknown variable on one side of the equation side and everything else on the other side. So how do we do this? Let's multiply T1 to the other side on both sides, and then let's divide the whole entire right side by itself. So something you can do is if you're multiplying a fraction or dividing by a fraction, you can just flip it on the other side. So we have this one. So on this side, it's 500 milliliters over 30 degrees Celsius. All right, units cancel. So now down to temperature is equal, T1 is equal to 300 times 30 degrees Celsius over 500. All right, a little bit of multiplication here. 300 times 30 is equal to 9,000 over 500. You can cancel out some zeros. Then 90 divided by 5 is 18. So our original temperature, or T1, that we solved for is 18 degrees Celsius. One medical application of the gas law is use in anesthesiology. When calibrating a gaseous mixture, it is important to monitor the pressure and temperature of the gas anesthesia being administered to patients. The ideal gas law allows for anesthesiologists to do this quick adjustment. For example, at sea level, the pressure is about 1 atmospheres. However, in some places at a high altitude like Colorado, the air pressure is about 0.85 atmospheres. This change in pressure has a large effect on the amount of anesthesia molecules that are being administered to a patient. It is very important to get the anesthesia amount correct to make sure patients don't wake up and they wake up on time. In summary, we learned that ideal gases don't exist, but they are very helpful with understanding gases on Earth. We also learned about the ideal gas law, or PV equals nRT. We learned about the ideal gas law constant R, and that units are very important and must be canceled out across the equation. We then learned about Boyle's law, or P1 times V1 equals P2 times V2. We then learned about Charles' law, V1 over T1 equals V2 over T2. And we finished up with understanding how these gas laws are very important in medicine, and more particularly in the operating room, through anesthesia that's given to patients to help them relax during the surgery and wake up when they're done. Thank you for watching Chem Talk, and this is your video about ideal gas laws. Make sure to like and subscribe, and check out any other videos on our YouTube page.